Okay, so let's get started. So from here on out, we will be in this room. I was able to reserve it for the next, all 3 sessions next week. So we are done trekking up the hill. The things I want to do today, 1, if there's any questions in the project, I'm always happy to answer those. 2, I had a question about what will be on the next quiz. 3, we are going to talk more about virtual machines. Now, unfortunately, there is no chapter in our book about virtual machines and virtualization. So I'm actually just recording these lectures. If you want a reference to go back to later to help study, in addition to the slides, I will put the lectures up on YouTube. I don't honestly know how good the sound quality is because it's just a computer sitting in front of me and I tend to wander around. But I will, at least it'll be there and it may help as a resource. So first up, any questions on the project? There were some questions posted overnight about exactly what format to print, and I answered those questions. So you should definitely check the top of the project page to look for clarifications on some ambiguities. I've talked to the TA. The project 4 grades, I think, are coming out today. And we're going to work hard to get tests for this project out on Monday. His goal is to really have everything ready to go, so grading goes pretty quickly on this project. And I've also talked to the TA who grades the quizzes, and I've sort of pushing both of them to grade things very quickly. So we can get your final grade without your class grade without the final ready as early as possible, so you can decide whether to stay around for the final. So I'm hoping to have everything graded by the weekend after classes get out, by the end of classes. So that being said, are there any questions on the project that people have right now? No. Okay. So there's a question about what will be on the next quiz. Our last quiz is next Wednesday. As with our other quizzes, it basically covers all the material since the previous quiz. So it will cover deadlock. It'll have a little bit more on monitors and condition variables. So I may ask you to write some condition variable code. The last time it was sort of reading code here. I wanted to basically give you the opportunity to get some practice in the project of using condition variables before I asked you to do it on a quiz. So hopefully by next Wednesday, given that the project is due Thursday, you'll have some practice. So there may be a question there. Though deadlock will be on it, and also virtual machines and virtualization. And then on Tuesday, there'll be a lecture on distributed file systems. So there could be a question on distributed file systems also. So it's a decent amount of material that kind of, when we have quizzes that are 2 weeks apart, there's sort of more material that rolls up into it. So are there any questions then? Yes, Scott. Do we have what? The solutions to the last quiz, I think, are up there. I'm pretty sure they're on Moodle already. I thought I saw quiz 6 solutions, but which I didn't actually post, which surprised me. But I think they are there. So the TA must have posted them unless they snuck out and some student posted them for everybody. Seems less likely. Maybe I did it. Do you see them? Yeah, so let's see. Oh, the final thing is, as you know, at the end of the semester, I'm sure everybody recognizes these red envelopes. So I have learned to not do evaluations on the last day of class because a lot of people have already started enjoying their summer by then. So we're going to do them a week early. So we'll end lecture a little bit early, and then we'll do course evaluations. So unless there are any questions, we will get started. Hopefully this whiteboard will stay in place. So we were talking yesterday about virtual machines, and we were talking about the basics of how virtual machines work. So we said you have your hardware. So we have our normal hardware. Normally our operating system would run right here and directly control all the hardware. When we're doing virtualization, we're going to run a virtual machine monitor here instead. And the virtual machine monitor now will manage all the hardware and control who uses the hardware then. On top of this, it will create what's called a virtual machine, where it basically emulates all the hardware, any privileged access to hardware. Non-privileged access, executing normal instructions, referencing normal memory. directly executes on the CPU, but privilege access causes a trap from the virtual machine into the virtual machine monitor. The virtual machine monitor can then emulate whatever privileged operation the code was doing. If it's disabling interrupts, for example, it might set a flag saying, I shouldn't deliver any interrupts, and then return. If it's doing I/O, it may sort of take whatever I/O is happening and then send it to the real device. If it's manipulating a page table, it may manipulate its own page tables accordingly to reflect what the virtual machine is trying to do. So this is the essence of how to do virtualization. And then within this, we can run a guest OS, and we can run applications. So the reason this is nice, this is a whirlwind tour, is that we can run multiple operating systems. So if you want to run Windows NT 4 because you have some application that hasn't been updated since 1995, you can run an older version of Windows here for compatibility. If you don't want to make, for example, if Microsoft wanted to change Windows so it wasn't compatible with old applications, they could use this as a way to run old applications. And in fact, they do. In Windows 7, they use a virtual machine in this way to run Windows XP applications in some cases, or Windows NT applications. The other really nice thing is these two operating systems can't talk to each other because they're like processes where every piece of hardware they reference is separate. So if you have some virus or malware running in here, it doesn't affect what's going on in here because this virtual machine can't access this virtual machine here. They have different sets of virtual hardware, and so they really don't interact. So the key difference is in a normal operating system, the default is to make everything shareable. Shared memory, shared files. In a virtual machine, basically nothing is shareable. So you can't directly share any kind of data by default. And if you want to share data, it's incredibly difficult and painful and slow. So it leads you to not share anything and have nicely isolated, somewhat secure installations from each other. Okay, so this is the basics of sort of how virtualization works at a high level. And we were diving into how to actually make it execute. Any questions on this top level picture? No. Okay, so we're going to go through basically how do we actually virtualize these three kinds of resources. And we started off talking about the CPU, and we said the key technique was trap and emulate. And the core recognition is anything that is a privileged operation, such as executing a privileged instruction to change the page table or to set an interrupt vector or something like that, will be illegal in user mode. So if we run the operating system kernel in a non-privileged mode, the processor will automatically trap. The other thing you need to do here is if there's data that sort of affects low-level things, like the data that actually holds the table of interrupt handlers, we need to make that data invalid or read-only or have a copy or something like that. Because we want to know when is the guest operating system trying to change the set of interrupt handlers. So we know where interrupt handlers should go. So if there's memory that is writable that really only the OS should write, such as memory mapped I/O, we'll mark all that invalid or read-only so that we can trap into the virtual machine monitor. So this was all well and good, but then we had this problem of sensitive instructions. And these are instructions that have different behavior in kernel mode and user mode. So they do different things, but they don't actually trap in user mode. So the instruction, when executed in user mode, does the wrong thing, but it won't trap into the VMM, so the VMM can't sort of emulate it and do the right thing. And the example we had was this push flags, pop flags, where in kernel mode, you can use this to disable interrupts. In user mode, the interrupt flag is just enabled. So this is where we left off yesterday, and we're trying to figure out how can we virtualize an architecture that has sensitive instructions. We would like to sort of run code natively, but then get control into the virtual machine monitor when it's doing a privileged operation. So these sensitive instructions can be privileged operations, so we need to figure out what we can do about that. Okay. So, solution number one was the bad solution, which I always lead off with, which is whenever you're in kernel mode, emulate every single instruction, because you can't tell whether an instruction is a regular instruction, a privileged instruction, or a sensitive instruction. If we emulate all instructions, then we can emulate sensitive instructions correctly. And as I said, this was done by Virtual PC. And this works, but it's slow. So it's good enough if you have a fast machine to run an older operating system built for a slower machine. So if you want to run, code from 1995 on a new machine, this is fine because the code expected a much slower machine. But you wouldn't want to sort of deploy your servers on it, your web servers or databases, because it would be much too slow. So anybody want to suggest other things you could do? And to some extent, the things you can do depend on what company you are and what you control. And we'll see how that works out. So any suggestions on how we can solve this problem of sensitive instructions that have different behavior? So, yes?
Could you just emulate those?
Okay, so we would like to emulate just the sensitive instructions. How do we find them? So that is a great thing to do, and that would work really well. The challenge is, remember, we're just executing normal code. The process is just fetching instructions from memory, executing them. These instructions look like normal instructions. So push flags and pop flags is a totally normal thing to do. It's only when the flags actually have the interrupt disable bit set that it's not safe. All the other times it's just fine. So how can we identify the particular use of these sensitive instructions we care about? Any thoughts? So one thing you can do is called binary rewriting. So this is the technique that VMware uses, or used. And what they do is their virtual machine monitor does not directly execute kernel code. What it does before it executes any kernel code, it actually scans the code it's about to execute, and it looks and says, does this code I'm about to execute have any sensitive instructions or privileged instructions? And then it rewrites the sensitive instructions to do something different. So if you had some code that was something like, so here's some code that pushes the current flags onto the stack, pops the top of the stack in the EAX register, sets the 1 bit in the EAX register, pushes the EAX back on the stack, and then pops the flags again. So this is code that could be risky, that is sensitive because we are popping the flags and we might be disabling interrupts. So what VMware would do here is they would take this code and they would rewrite it so that what they would do is they would rewrite the code to insert an instruction that will force a trap into the hypervisor, into the virtual machine monitor, sorry. So they'll modify the code to explicitly trap into the virtual machine monitor. The virtual machine monitor can then emulate the popf instruction the correct way, and it will return, and then code will continue. So it means that when you're executing kernel code in this solution, you're not executing the kernel that Microsoft built or that is built by Linux or by Apple, but you are executing a modified version of that where all these sensitive and privileged instructions have been rewritten to do things better for virtualization. So the nice thing about this, for example, is you know, maybe we don't actually have to trap into the virtual machine monitor here. Maybe we can just say, instead we'll just set a interrupt disabled flag that the virtual machine monitor can check before it actually delivers a virtual interrupt. So we can actually even make this faster than trapping because we don't always have to trap for all of these instructions. Because some money uses of instructions might be benign and safe. We only trap when we only sort of do something special when we have to. So this works out well. It's complicated to do, and really only VMware does this because being able to scan the kernel, find all these sensitive and privileged instructions, rewrite them, and make sure the resulting code runs perfectly, just as a real processor would, is hard. And part of the reason is that Intel has not actually documented what a real processor works. There's no manual that says this is what x86 means. And they want it that way because they don't want AMD to copy it. They want it to be a little bit murky as to how every instruction works. And in fact, their definition of x86 is their internal emulator. If it runs on their emulator, then it's x86. If it breaks on their emulator, then it's not x86. Okay, so this works. And this is good if you are, the nice thing about this is you don't need access to the operating system. You can run any operating system because we're just going to scan the kernel code and rewrite it. You don't need to modify the processor architecture because we're running on a totally normal x86 CPU. All you need is this fancy technology to scan the code, disassemble it, change it, reassemble it, and then run it. Okay, other possible solutions. What if you were Intel and you wanted to make, you thought virtualization was a good thing, you wanted people to use it, what could you do as Intel? Alfred.
You can have a branch in that code.
You can have what?
Like a branch.
Well, so this code is written by Microsoft, so Intel can't change this code. So what they can change is they can change the processor. So if you could change the processor, what would you do to fix this?
Well, you could enable the VM, the virtual machine monitor, to assign the I/O devices to specific operating systems.
Mm-hmm. So that when we get to devices, we can talk about that particular thing. But in this case of dealing with sensitive instructions, is there something Intel could do? Because remember, the problem is these instructions have different behavior in user mode and kernel mode. So what Intel can do is they can actually modify the architecture and make the instructions do the right thing so that they don't have different behavior. And the way Intel did this is they added something called ring -1. There used to be ring 0, 1, 2, 3. Now there's a ring -1. And in ring -1, what this means is the kernel can still run in ring 0, where the behavior looks like it's doing the right thing. There is still a ring 3 where the behavior does the ring 3 behavior, but now in ring -1, you can control what happens to these instructions. So one option Intel provides is they actually have a separate set of virtual flags. So in this case, if you change the flags, you change these virtual flags, but the real flags don't change. So they basically provide the functionality the VMM was doing in software and hardware, having some virtual hardware built into the processor. And then the virtual machine monitor, if it wants to, can do something with these virtual flags. It can say when it's about to deliver an interrupt, oh, is the interrupt disable flag set in the virtual flags? And if so, do something special. The other thing that you can turn on in some cases is you can make sure that all sensitive instructions always trap to the VMM so they do the right thing. And this only happens if you're using ring -1 if you've actually sort of turned on ring -1 for virtualization. If you leave it turned off, this doesn't happen anymore. So the idea is if we have a problem with the architecture not being virtualizable, we can fix the architecture so that it becomes virtualizable, and that all the instructions do the right thing. Okay, what if you're Microsoft? So this is how a third party like VMware can solve it. This is how an undergraduate architecture student can solve it using an emulator like Gem 5. This is how Intel can solve it, or AMD. What about Microsoft? They control the operating system. Any thoughts? Yes?
Redirect syscalls from the platform for the code that you're running to the proper code the proper syscall that the current actual running operating system is using.
Okay, so you're saying instead of actually running the kernel up here, so you basically get rid of the guest OS here and have system calls go right to the VMM. So this is actually done, this is a different style of virtualization called vServers or containers, where you have applications that look like they're running their own operating system, but really they're sort of a single global operating system underneath it, but the apps don't know about it. So that works, but that doesn't solve it if you want to run Windows down here and you want to run Linux and Windows, because you can't, there's no kernel that can handle system calls from both of them. So it only works if you're running all copies of the identical version of Linux. So remember, the problem here is that the operating system expects a different behavior of these instructions in kernel mode, right? And so what we can do is we can change the operating system to not expect that behavior. So if the operating system doesn't use these sensitive instructions, then there's nothing to worry about because there won't be any cases where the wrong thing happens. So typically how this works is just the way user mode code invokes the operating system using system calls. In these other cases, in trap and emulate, the way an OS invokes the VMM is by trapping on some privileged instruction. What we can do is basically replace privileged instructions with what's called a hypercall, which is a call from the OS kernel into the virtual machine monitor. So anytime you want to disable interrupts, enable interrupts, do anything else that is sensitive, instead of having code that does that sensitive thing, we will just make an explicit call into the virtual machine monitor and say, do something for us. So the nice thing about this is, if you have source to the operating system, there's not that many lines of code that actually do these kinds of privilege-sensitive things. It's not that hard to do. And it can be a lot faster because you can sort of have hypercalls that do multiple things at once. Normally, in hardware, instruction does one thing. But you can have a hypercall that says, like, send a packet. So instead of saying, write the packet address someplace and then set a descriptor flag and then write another bit to a device register, you can just have a single hypercall send packet, and it does everything. So this can be a lot more efficient than sort of trap and emulate style virtualization. The downside is you have to have source to the operating system and you have to modify it to pull this off. This is called para-virtualization. So these approaches up here are called pure virtualization because you can run an unmodified operating system and it just runs correctly, everything works, the performance may change. Here you need a modified operating system for it to work. So you may have heard there's a virtual machine monitor called Xen, X-E-N. It was started as a research project at Cambridge University. Their goal was to deploy applications into the internet where you have sort of a machine at every university that was running virtual machines, and as experimenters you could upload your code to run in other people's places. So you could build content distribution networks and multicast services and all kinds of great stuff. And they took this approach, and it was remarkably easy, and they released the code and started a company around it that was bought by Citrix, and Amazon now uses Xen as their cloud computing base. So Xen, which sort of took this approach, is now deployed on like 300,000 machines at Amazon. So these all have value, but again, it depends on who you are and what you can do. If you have no access to anything, you're sort of limited to these approaches because you can't modify the hardware or the OS. If you can modify the hardware, then you can make virtualization software pretty easy. So Intel and AMD do this. If you only have access to the operating system, then you can change this. So the way things currently stand is that most virtual machine monitors actually do all three of these, because there's some cases where rewriting is actually faster than these other choices. So for example, this disabling interrupts, if we can do it in software with a single function call, that's faster than trapping into the virtual machine monitor or doing something. So VMware, depending on the processor, will still do binary writing. This is the sort of simplest approach. So this is how Zen works most of the time. This is how KVM, which is the native, this is sort of the built-in Linux virtual machine monitor called KVM, uses this approach. Microsoft's Hyper-V, I believe, uses this approach. This here, modifying the operating system, is also used by all these systems, and it's used particularly for I/O. So instead of emulating a particular network card, people have a virtual network device that will, sort of with a single hypercall, send or receive a packet. It just makes network I/O and disk I/O a lot faster. But so these are the general solutions on how you solve virtualization. Any questions on these range of options? So actually one quick thing to note is if you look at IBM or you look at Oracle, so IBM makes these servers that use a Power 7 processor, they write the operating system AIX, and they write their own hypervisor. As a result, they do para-virtualization because they control all three things, and so they actually modify the OS to do certain things, they modify the hardware to do certain things, So actually, I guess they do a combination of these two. So similarly, what used to be Sun Microsystems, now Oracle makes their own chips, the Spark chips. They have their own operating system, Solaris. They modified Solaris to basically use hypercalls any place instead of privileged instructions. And then they modify the hardware to do a few special things to speed it up. So if you control the OS and the hardware, then you take these two approaches. It's only when you don't control everything that you have to sort of choose one of these three on its own. Okay, so that covers sort of virtualizing the CPU. Any questions? So I take it there are no questions on it. So let's look now at virtualizing memory. So when we think about virtualizing memory, if you remember back to March or something, we looked at virtual memory. So we have physical memory, which is made up of pages. The OS would create a page table, which would map virtual addresses to physical addresses. So the guest operating system wants to think it has some kind of physical memory, and it wants to map its own virtual addresses for its processes to physical memory. The problem is that we now have multiple guest operating systems that are doing the same thing. Right? So we can't actually give physical memory. We can't sort of say to each guest operating system, you have all the physical memory. What we would like to do is to say, let's let the virtual machine monitor virtualize memory just the way the kernel virtualizes memory. And then we will basically, instead of giving the kernel a physical address space to then do address translation on top of, we'll give it a virtual address space. So we're going to have two-level address translation is how people typically do this. So what this ends up looking like is, we have physical memory. We then for each virtual machine, we're going to have a page table, and we're going to have mappings from the set of addresses that are presented to the virtual machine into real physical memory. The idea is we're going to present these virtual addresses to the virtual machine as if they were physical addresses. The virtual machine then will run multiple processes, and each of these will have their own page table. And these page tables will map the virtual addresses of processes into what the operating system thinks is a physical memory, but is not. And then the virtual machine monitor will map the addresses that the virtual machine thinks are physical into the real physical memory. So this is kind of mind-bending and very complicated to think about and to keep straight, because we now have virtual addresses, we have physical addresses that are really virtual addresses here, and then we have real physical addresses. So there's some terminology. We're going to call these host physical addresses, because these are the real physical addresses on the host computer. We're going to call these guest physical, because these are what the guest virtual machine or the guest operating system thinks are virtual or physical addresses. And then we're going to have guest virtual addresses in processes here that map to guest physical addresses, and the guest physical addresses map to host physical addresses. So the basic translation mechanism here then is given a guest virtual address V, look it up in the process page table. To find a guest physical address. So we're doing one lookup in the page table to go from virtual address to guest physical address. And then we're going to take that address and look it up in this page table here to find the real physical address. We have to do this on every single memory reference, because every reference in the guest OS goes through virtual addressing, so we need to go through the guest virtual page table and then the VMM's page table. So there's a problem here, which is that processors don't have page tables like this, right? A processor will only look in one page table on translation. We learned about TLBs. On a TLB miss, you look at the page table and populate the TLB. The problem is now that doesn't work anymore, because if we look at the address in this page table, it'll produce the wrong physical address. If we look it up here, we're using the wrong virtual address to look things up. So with normal processors, we cannot sort of do this except by emulating every single memory reference, and for every memory reference in software, doing this two-level lookup. So how can we speed this up? So again, just as there was with CPU virtualization, with memory virtualization, there's really three approaches. And it depends on who you are as to how you want to do this. So the hardware approach says, we said there's a problem because processors can't do two-level lookups. Let's just make processors do two-level lookups, right? Easy problem to solve. So Intel and AMD have done this. AMD calls it NPT for nested page table. Intel calls it EPT for extended page tables. And effectively, all it says is that when you're running in ring -1, you can install a second level of page table. And then when you're running any code in a virtual machine in ring 0 through 3, addresses are translated first through the page table controlled by the guest operating system, and then by the page table controlled by the virtual machine monitor. So this all happens automatically. You just have two page tables in hardware. So there is actually a substantial problem here, which is TLB misses. So if you think about, remember what page tables look like. That page tables are actually trees, right? We had this tree of multi-level page tables where we translate some of the address in each tree. What this means now is when you miss in the TLB, so we have a guest virtual address, we look it up in the TLB, we couldn't find it, so we now need to go to the guest page table to translate this. So to go to the guest page table, we have to look up the base of the guest page table. Well, this is an address that has to be translated. So this has to go through the TLB also, or some kind of TLB. We then need to look up the next level here, and this has to go through the TLB to do a lookup. And when we look up, the next level of the page table here, we go through the TLB again. So we now are sort of accessing the TLB during address translation to find extra things. So we're now putting more things into the TLB, so there's less space in the TLB. The second problem is, what if when you're looking up, you're trying to translate, this is the guest operating system's page table. Suppose that the guest physical address for this page table is not in the TLB, right? So what this means is, to reference right here, we're going to go through if we can't find the guest physical address for this page table in the TLB, we're now going to have to walk the VMM's page table to put this into the TLB. So we're again going to walk through a page table. The net result of this is that on a single TLB miss, for every level of the guest page table, you may have to walk all the levels of the VMM's page table. So it used to be something like 3 memory references is now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, something like 12 memory references to refill the page table. Because we have to translate every level of the page table in addition to the address itself. So one way to make this, one thing that happens here that I didn't bring up earlier that I should have brought up is that when you use this approach, what goes in the TLB is the result of the 2-level translation. So normally we will put in the TLB the translation all the way from the guest virtual addresses up here all the way down to the physical memory. So we do both levels of lookup, and we put the combined result of everything from here all the way to here into the TLB. So that when we hit in the TLB, it's just a normal hit and it goes at normal speed. It's only when we miss in the TLB that we have to potentially walk both page tables to fill it in. Does this make some sense? So remember, the guest page table is in the guest physical address space, and this is actually virtual memory, right? Because the guest physical address space is translated by the page table from inside the VMM. So to translate these addresses that the guest thinks are real physical addresses, but are actually guest physical addresses, we need to go through this page table to translate them. So these are, normally the page table in x86 is stored using physical addresses and doesn't need to be translated. But in this case, because everything inside the guest virtual machine is stored using virtual addresses provided by the VMM, it needs one more level of translation. And so we end up translating all of these references to all the levels of this. And you end up with a very slow, potentially a very slow operation to refill the TLB. So the takeaway from this is fast when you hit in the TLB, but when you miss, it can be kind of slow. But you don't really need to change the operating system to pull this off. Yes?
Since you have multiple guest OSs, would you have the same guest virtual address for most of the guest OSs?
So guest virtual addresses these are just like process virtual addresses today, right? So you have multiple processes, they reuse the same virtual addresses. Every process has an address 1000. And here it's every process in every guest OS has an address 1000.
So you have more chances of conflicts when you switch between the OSs that you're running, right?
So it's true when you switch between OSs. So just as you have to flush the TLB when switching between processes, you have to flush the TLB when switching between virtual machines because the addresses could get reused. So actually, Intel added some hardware to keep track of for every TLB entry which VMM it came from. So it wouldn't have to flush the TLB in that case because you're right, that can be expensive. Okay, so this is what you do if you're Intel. So the Zen solution, remember, is the paravirtual solution. So the paravirtual solution is, well, if we can modify the operating system and the VMM, but we can't modify the hardware, what could we do? And their solution was first, the VMM is going to have a special way of actually showing the guest OS. Basically, it's going to show the page table to the guest OS. So the VMM will basically give the guest OS and some piece of memory a mapping of guest physical addresses to host physical addresses. So the VMM the guest OS now knows exactly what is the host physical address for a given guest physical address. So the guest OS now, when it builds a page table, instead of putting guest physical addresses in its page table, it will put real host physical addresses. So it will do the translation itself from guest physical address to host physical address before it builds the page table in some other data structure, and then put the host physical address into the page table. And the VMM, though, because it's letting the guest use real physical addresses, there's a problem that a guest OS could use a host physical address that doesn't belong to it, that belongs to some other VMM, virtual machine. So the VMM, whenever the guest builds a page table, the VMM has to verify that all the physical addresses being used belong to that VM. And it does that by making the page tables non-writable. So if the guest tries to write to the page table, it tracks the VMM. The VMM checks that the address is correct and then actually inserts it into the page table. So the solution here the solution was that the hardware would do the second level of translation. The solution here is that the guest operating system does the second level of translation as part of building page tables. So every page table has the complete two-step translation in it. So the VMware approach is to do what's called shadow page tables. So here I'm going to draw it a little bit in the opposite direction. We have So we have these two steps of translation. We then have a hardware TLB. So the challenge VMware is thinking about is the hardware TLB needs a pointer to a page table. It has to point to some page table to automatically look things up in on a TLB miss. So we can't use this page table right here because it translates the wrong things. We can't use this page table right here because it translates the wrong thing. So the VMware solution is to use a shadow page table. Every time the shadow page table starts out completely empty. Every time the guest references something, the guest process references something, it'll take a TLB miss, it'll check the shadow page table, it's empty, it'll trap. The trap goes into the virtual machine monitor. So now the VMM is in control, and it has to figure out what to put into this page table to satisfy this TLB miss. So the virtual machine monitor now knows about its page table. It knows where the guest OS page table is, and it will do the translation from both across both page tables and compute the mapping of guest virtual address to host physical address. And it will insert the host physical address into the shadow page table. The TLB then will suck this out of the shadow page table and fill in this appropriately. So this is very similar to what the hardware was doing. In this model, the hardware was walking both page tables and filling the TLB. Here, the VMM is walking both page tables, but instead of filling the TLB, it's filling the shadow page table. So once it's in the shadow page table, the TLB can automatically reference things again and again. So as your process runs, more and more of this gets filled in. And so you stop having as many TLB misses. You stop missing in this page table as often. And the nice thing is, in this model, if you miss in the TLB, this is just a normal page table. So it's a normal cost of a TLB miss. We don't have to do this very expensive two-level TLB miss once we put something into the shadow page table. So again, this is what you do if you can't control the hardware and you can't control the operating system. You do something in the middle. Coach it.
It seems to me like the Zen approach might be faster than the VMware approach. Why do you do?
So the Zen approach is faster, but you need to modify the operating system. And so if you want to run Windows, which is a fairly common thing to want to run, you can't do this. And so it turns out in Linux now you can compile for Zen directly. So the Zen features to do it this way are built into Linux. Most people, though, because there's hardware available, use this approach at this point. Although VMware has some nice numbers that say depending on which processor, this can be a lot faster than the two-level translation for some processors. Because this, for certain programs, these sort of multiple level misses are really expensive. And the shadow page tables, once you build them, are really fast. The downside here is that anytime the guest OS changes the page table, we need to invalidate the shadow page table. Because when this translation changes, it changes the mapping from here to here, so we need to remove it from the shadow page table. So so that means that the guest page tables are all marked read-only, and if the guest OS tries to write to it, it'll cause a trap that lets the VMM invalidate the page table. The other thing this means is that page faults get kind of complicated. So a page fault happens now, when the TLB references the shadow page table and something isn't in the shadow page table. So we have to figure out why is it not in there. So we first trap to the VMM and we have to figure out why is the entry not in the shadow page table. So one option, did I write the right thing, is that it could be that the VMM hasn't yet allocated memory for this guest physical address. Right? So there's some guest physical address that we're referencing, and in this table, it's invalid because we haven't assigned physical memory to it yet. So if this is the case that this guest physical address to host physical address reference is invalid, then we basically fix up the guests, the VMM's page table by allocating some memory, marking the entry valid, let it continue. Another option is that this is valid, but so it could be that in this page table right here, the entry for the address isn't present. So if this isn't the case, the VMM has to basically insert a virtual page fault by jumping to the page fault handler in the guest OS, setting it to the appropriate processor mode. The guest OS now will So the guest OS does the totally normal things it does for a page fault, check if it's a valid address, allocate some memory, fix up the guest page table, and then it will return. And then at this point, this updating the, sorry, take it back. So when it tries to update the guest page table, the page table, remember, is read-only, so this will track to the virtual machine monitor, which will then update the shadow page table. And then when it returns, everything has been mapped again and things continue. So you can see how page faults can get pretty slow because you have to potentially call through both, have the virtual machine monitor, check if it's a page fault, and have the guest OS check if it's a page fault in some cases. So any questions on how to virtualize memory in these three different ways? So as I said, this is the technique most people are going to because doing it in hardware is just a lot simpler because in this model, we know if the page fault is from which page table the fault is from, and we know the processor knows where to deliver the trap, to send the trap to the VMM directly. If it's in the VMM's page table, send it to the guest OS. If it's in the guest OS page tables. So I have about 4 or 5 more minutes before I want to do course evaluations. So we'll talk about virtualizing devices. Actually, I want to talk about something else first. I want to think about it. So one kind of virtual machine monitor is called a hypervisor. And this is what I've been talking about before. You have virtual machines. You have your virtual machine monitor. And then you have your hardware. So what this means is that all access to the hardware always goes through the VMM. So if we want to have any drivers, the drivers sort of run in the VMM that actually talk to the real devices. So this is nice if you're using sort of all these virtual machines equally. But what if you have a desktop computer and you want to mostly use Linux and occasionally use Windows? So this is called a Type 2 virtual machine or a hosted virtual machine. And in this model, So in this model, we are running what's called the host operating system. This is the normal operating system you use most of the time. You use it for most of the things you're doing. But then you also have some virtual machines that you run. VMware Workstation, Parallels, VirtualBox, QEMU all have this model. So in this model, the host OS controls the hardware, not the virtual machine monitor. So when the virtual machine monitor needs some physical memory to allocate to a guest OS for filling in one of these page tables, it'll go to the host OS and say, can I allocate a page of memory? If it wants to send a packet, it doesn't run drivers over there, but it'll just use a system call or something like that to call into the host operating system and send a packet through the host operating system drivers. So the host OS is in control, and it basically runs the VMM as another process. When the VMM runs, it may monkey with the hardware to set up nested page tables, and all things happen, but when interrupts come in, it switches back to the host OS, and the host OS handles all I/O. So the host OS is still in control, and it just thinks of the VMM as one process that it's running. Or it might think of each guest VM as a process that it's running. It isn't really aware, it isn't really sort of ceded any control of the system. So the benefit of this approach is that it's potentially faster because you can just kind of go into the VMM and write through the VMM. The downside is that you pay the performance cost for everything that you're doing. So nothing runs at full native speed because we've got the CPU virtualization traps that we have. We have this extra address translation cost. In this approach, the things you run natively run at full speed in the host OS. But when you run the virtual machine, things in a virtual machine, they're a little bit slower. Because now we need to call from the VMM into the host OS, and then we have to go through the host OS. And in some cases, it actually calls into user mode in the host OS, and then the user mode program will call into the kernel. So you've got extra crossings. It depends on if the virtual machine implementers want to write kernel code or user mode code. User mode code is a lot easier but slower. So these are the basic types of virtual machines. And they're both widely used. This is used in data centers for servers. This is used on desktops and laptops and things like that. Any questions? Okay, so I'm going to stop here. I know I wanted to get to device I/O devices, but I didn't.